got into maritime continent work because I was looking around for PhD projects and I found one that looked interesting, which was on the maritime continent, and I've just stayed working on maritime continent ever since, really.
I see. So I think you
Into
this
maritime
is
work.
very unique country or unique area or
Really,
complicated
yes.
phenomena or
Yeah,
mainly multi-scale.
I mean everything really about it, and so when I was looking around for jobs last year and I saw one in Singapore, I thought that was the perfect opportunity to move to the maritime continent and
Nice.
see maritime continent weather up close.
Okay.
Okay. Now it's
Udah.
already
Okay, okay.
9. Yeah.
Enough. Thank you.
Thank you.
And we already live in YouTube actually.
Okay.
It's shall we maybe wait for 1 or 2 minutes probably just to get the audience? Maybe they're just checking in right now,
Okay.
Oh.
and then we will start right away.
I'm sorry, Dr. Simon, where do you come from? From UK, yeah, from Australia, or?
So I'm from the UK. I most recently was living in Leeds, working at the University of Leeds, and before that I was at the University of Reading. And my PhD was at the University of East Anglia, UEA, which was with Adrian Matthews.
So you together with Dr. Andreas Matthews, yeah, and Dr. Andreas Matthews,
Adrian Matthews.
yes.
Yes.
Is he your supervisor last time? No.
He was my PhD supervisor.
Okay. Cool.
Good
The
morning.
famous scientist. I
Yep,
think you come from Reading University, not.
Pak Didi.
Yeah, good morning, Simon. Good morning, everyone. Pak Yuda.
Hi.
Pak Didi.
Yes, it's good to see you again after the last Terra Maris
Yes.
meeting.
Yes.
Yes.
So you've met Pak Didi, Simon, and you met in a meeting before?
Yes, I mean you were involved in Terra Maris, weren't you? And
Yes.
I will mention the Terra Maris briefly later on. That was supposed to be a field campaign, which unfortunately never happened.
Yeah.
So I was involved in the planning for that, and I would have been on the field campaign if it had gone ahead.
Okay. All right. I think we can just start the forum. I mean, there will be an introduction from me, so enough time probably to also wait people to join us. Okay. Maybe we should start. Okay. Good morning, everyone. Welcome to Kolokium PRIMA with me, Yuda Setiawan Jamil, senior researcher in the Research Center for Climate and Atmosphere under the Research Agency, Innovation and Research Agency of Indonesia. So today our title for the talk today is about physical processes in scale interaction of convection over the maritime continent. And the speaker will be Simon Peatman. He's already here with us. And just a brief introduction of Simon Peatman. Gonna tell a little bit of story where I come across his paper even before I did my PhD. And it was at 2010, there's a workshop and I met Joshua Kian. And I told Joshua Kian how I did MJO work and in Malay Peninsula. And then Joshua asked, so which one comes first, the rain or the MJO? And I was very confused of that question because I analyzed the radio sound data, not the rainfall. So I cannot answer him. And at that time, later on, I start to look at the rainfall, and I start to see that the rainfall actually comes earlier, even before the OLR picks up. And it's pretty confusing until in 2013, I think your paper start to get published online, is it?
Yeah.
That paper pretty much gave a clear picture of what the real problem is. And nowadays we know that as the vanguard effect of MJO. And I think it's one of the milestones in the MJO study over the maritime continent, where after that, a lot of picks up on the study of the diurnal signal in the maritime continent to try to explain the MJO, and also inspired several campaigns such as the Year of Maritime Continent and so on. And nowadays, Simon himself, of course, there's a lot of things that he had already done from that time until right now. So there's be more things that he going to share with us, and I think it's gonna be a treat for us, for everyone here, to listen directly from Simon Peatman himself. And let's join me to welcome Simon Peatman to Kolokium PRIMA. So Simon, you have 45 minutes to 1 hour for the talk, and then the rest of the time we will use for Q&A.
Yeah.
So please, Simon.
Thank you very much. Okay, can you see my slides correctly?
Yes.
Yes, great, thank you. Okay, so as Yuda says, this is a talk on the physical processes in the scale interactions of convection over the maritime continent. And in fact, his introduction that he gave there is very useful, because I'll start by talking a bit about the vanguard effect, and then work that I've done kind of following on from that. So to begin with, just a schematic diagram which shows some of the various large-scale drivers which influence convection over the maritime continent. And the main one I'm going to be talking about in this talk is the MJO, but I'll also allude to some of these other phenomena seen on here. And really the kind of the picture that I want to, the scene that I want to set here is to make clear that when you're thinking about convection in the maritime continent, you really need to think about phenomena happening across a range of spatial scales and a range of temporal scales, and how those different phenomena interact with one another. And that's what we mean by scale interactions. So the biggest form of variability in convection, and the one that we kind of experience day to day, is the diurnal cycle. So this is from the paper which Yuda was talking about earlier. As he said, it appeared online in 2013, finally published properly in 2014. So this was the key result that came out of my PhD. So here is just a picture of the diurnal cycle. So this is composites of precipitation from TRIM 3B42, which is what we used to use before GPM iMerge came along. And so these are composites at each time of day. So you've got midnight local time on the bottom right, and then moving clockwise every 3 hours. So you can see you get this strong diurnal cycle, especially over the islands, with the peak in rainfall kind of in the evening and into the night. Whereas the diurnal cycle over the ocean is somewhat weaker. The exception to that is where you get regions such as just southwest of Sumatra or just northwest of Borneo here, where the ocean diurnal cycle is still quite strong, and that's because you've had the convection over the land that then propagates offshore. So this image that I've shown here is what we think of as the sort of canonical diurnal cycle. We think of this as the typical picture. But it's worth pointing out that these are only averages, and there's an average over several years that has gone into this. So each of the panels here firstly, is artificially smoothed by the averaging. So you wouldn't get any individual day that actually looks like this. In reality, it's a lot noisier. And also, it's important to remember that this diurnal cycle does not necessarily happen every day. It's something you see in the mean. And then a picture of the MJO. So again, this is something I'm sure we're all familiar with. So now I've got, using the RMM index, I've taken all days where the amplitude is at least 1. And I've again done composites. These are now anomalies for each of those 8 MJO phases, with phase 1 in the bottom left, and this time going anti-clockwise around the phase diagram. And so in blue, positive anomalies, we see the active MJO envelope, which propagates slowly eastwards across the region. And then along behind it, we have the suppressed envelope, which is shown in red. But what's key to notice here is that when you look at the maritime continent islands, they often have an opposite phase anomaly from the large scale. So here in phase 2, much of the maritime continent is within the large scale suppressed envelope, but you can see that you've actually got blue colors over most of the islands. So the active MJO rainfall over the land is in a different phase from over the ocean. So the land-based rainfall, the anomalies have kind of leapt ahead of this large-scale envelope. And this has become known as the vanguard effect, because it's like a vanguard of the MJO, which leaps ahead over the islands, but not over the sea. So then I was looking at why this happens, and it turns out that the key thing is the diurnal cycle. So to keep things simple, I modeled the diurnal cycle as something sinusoidal. So for every grid point in the domain, our precipitation R, I model as a daily mean value, which I've called R bar, plus a cosine. So RD is what I'm calling the diurnal amplitude. And then T0 is the diurnal phase, so that's the time of the peak rainfall. So if you look at the diurnal amplitude in this map at the bottom, in a climatological sense, this is showing you where you get the strongest diurnal cycle. So as I said earlier, this is mainly over the islands and places near to islands where you get propagation of the convective systems offshore. But if you think about how that changes with the MJO, here's an example, top right, where I've averaged over the island of Borneo. So the black curve is showing the mean diurnal cycle. So you can see that the rainfall is peaking about 6 p.m. local time. And then I've picked out 2 phases, MJO phase 3, which is a wet phase, and phase 7, which is a dry phase. And so you can see that in a mean sense, you do still get the diurnal cycle in both, but you can see that the diurnal amplitude has changed, where it's larger in phase 3 and smaller in phase 7. Although you'll notice that the diurnal phase barely changes, so the time of peak convection stays around the same. So the MJO doesn't seem to have an impact on that. But if we then look at how the diurnal amplitude changes across all phases, this is again an anomaly. So blue is showing where the diurnal cycle has a larger amplitude. Red is showing where it has a smaller amplitude. This doesn't show quite such a clear picture of eastward propagation, but you can see that for the most part, these changes in amplitude are similar in magnitude to the changes in the daily mean that we saw earlier. So if I just jump back a couple of slides, you can see this color bar ran from -5 to +5. I've used the same color bar here, and you're getting colors of similar intensity on the plots. So you get a modulation of the diurnal cycle that's similar in magnitude to the modulation of the daily mean. If we then think about how that diurnal cycle and daily mean rainfall are each varying as we go through an MJO cycle. So the scatter plot here, I've just picked out 3 grid points kind of at random from across the maritime continent. I've plotted daily mean rainfall on the x-axis and the amplitude of the diurnal cycle on the y-axis. And then the 8 data points on here for each are the 8 MJO phases. Then you can just do least squares regression through the points, and that gives you a gradient and a correlation coefficient. So if you plot the gradient for all possible grid points, which is panel A here, you'll see that in the places where the diurnal cycle is strong anyway, so over the islands, the gradient is very approximately 1, so sort of order of magnitude 1. So as you go through an MJO cycle, the daily mean rainfall and the diurnal amplitude of rainfall are roughly in a kind of one-to-one relationship with each other. And if you look at the correlation coefficient, and you just average over the places that have a strong diurnal cycle, you'll find that you get an R² value of about 0.8. So in other words, about 80% of the variability in the daily mean as you go through an MJO cycle can be explained by the variability in the diurnal cycle. So it's really the change in diurnal cycle as you go through an MJO event that is really controlling what actually happens to the daily mean rainfall in the places where the diurnal cycle is strong. And so to summarize all of this, if we now look at this plot, which has MJO phase along the x-axis, if you look at, firstly, I'm going to introduce TB, which is brightness temperature. So this is another satellite gridded data set. So if you take the mean brightness temperature over the land, which is the thin curve, and the mean brightness temperature over the ocean, which is a thick curve, you'll notice I've inverted the brightness temperature axis here. So the small values are at the top. So the cold brightness temperatures, when you're looking at cold cloud tops, so you've got intense convection, are higher up on the graph. So as we expect, over both land and ocean, we see the large-scale MJO envelope peaking around phase 4 or perhaps phase 5. So that's when the active MJO is over the maritime continent. Now, if you look at the two blue curves now, these are the diurnal amplitude for land and ocean. You'll see that both of those peak around phase 3. So the diurnal cycle doesn't peak in phase with the main active MJO envelope, which is in phase 4. It peaks a phase earlier. Now over the land, the diurnal cycle is very strong, and that's enough to drag the daily mean rainfall ahead of the MJO envelope as well. So the red short dashed line here is the daily mean rainfall over the land, and because of the influence of the diurnal cycle, it peaks earlier than the large scale envelope. And so this is the vanguard effect. Whereas over the ocean, the diurnal cycle is much weaker, and so it doesn't have so much of an effect. So the daily mean over the ocean, which is this red long dashed line, that still peaks in phase with the large scale MJO. So the vanguard effect is something that happens over the land and not predominantly over the ocean. Then we can start to think about why this actually happens. What are the physical processes that are going on that are responsible for the rainfall, and how are those changing? So a lot of the rainfall over the maritime continent falls from mesoscale convective systems, or MCSs. There's various approaches in the literature to identifying and tracking MCSs, and so you'll find a range of estimates as to how much rainfall in the region actually comes from MCSs. But looking at this particular paper, which was by a couple of researchers at the University of Leeds, Julia Crook and Fran Morris, and I was the PI on this project, we took one particular MCS tracking algorithm, which came from the University of Reading. We tracked MCSs over Southeast Asia for 5 years, and we find that during November to April, something like 45 to 70%, depending on exactly where in the region you're looking at, of precipitation comes from MCSs. So these are a crucial contribution. And in fact, in some regions, when you go to very extreme rainfall, you find that MCSs are particularly important. So these 3 plots at the top are showing for 3 particular regions. On the x-axis, percentiles of all rainfall. So for example, if you are in a day that falls into the 70th percentile of daily mean rainfall, what percentage of the precipitation comes from various sources? So in the blue, we have MCSs. In the orange, we have tropical cyclone attributed rainfall, and in green is everything else. So just to say, tropical cyclones, the way we defined that in this study was not just in the rain bands of a TC, which is why you might be a bit surprised to see tropical cyclone rainfall for Java. You might think a bit close to the equator. In fact, and indeed Borneo even closer to the equator. But in fact, what we've said is that any MCS that was tracked, any feature that was tracked that was within, I think it was 10 degrees of a TC center, And then any systems which split off from that, we attribute all of those to tropical cyclones because their ultimate kind of source was the TC. So even if you're looking at a system that ends up actually a very long way away from where the tropical cyclone was, we still attribute that to tropical cyclones. So you can see that for Borneo, if, as the example I picked out, 70th percentile, so something like 55% of all the rainfall falls from MCSs. And when you go to even more extreme days, if you're on a day that's in the top percentile of rainfall, it's more like 60% of that rain will be coming from MCSs. For Java, you really get a big increase. So on days where you've got extreme rainfall in Java, more than 3/4 of the rainfall is likely to be coming from MCSs. Of course, this isn't true everywhere in the maritime continent. So I've just put up the North Philippines, so Luzon, as an example of somewhere where it's different. There, of course, you're in the Northwest Tropical Pacific cyclone track. So there, when you go to the extreme rainfall days, it tends to be TCs that are contributing to those. But for a lot of the region, this is the picture you see. The MCSs are right up near the top of the plot. So they're important to consider. And we're going to think about how MCSs change during an MJO cycle and also during equatorial waves. So I've put here examples of 3 equatorial wave modes. So the equatorial Kelvin wave, the westward moving mixed Rossby gravity wave, and an n=1 Rossby wave. And then what I've shown here is an anomaly of just the MCS rainfall during an MJO cycle and during a Kelvin wave cycle. So the MJO is on the left. Here you see kind of some signs of eastward propagation in that phase 2, you've got the peak kind of over towards the west, and then it slowly migrates east over to sort of phase 5. It's not quite such a clear picture as when you're just looking at the entire MJO envelope. But you can see that the MCSs have pretty considerable anomalies associated with them, again, it's the same order of magnitude as we were seeing in previous plots. So the way that the MJO affects the amount of rainfall really is its effect on MCSs is a major way in which that scale interaction occurs. And the same is true, I've just put here the Kelvin waves. So we've defined here 4 different phases of a Kelvin wave. So the phase where you have low-level westerlies, where you have low-level divergence, low-level easterlies, and low-level convergence. And again, you can see this uses the same color bar as the other plot. Again, you can see there's a big impact on the MCSs as you go through a Kelvin wave cycle. So the variations in MCSs are a way in which the scale interaction between the MJO and the local rainfall occurs. And then a particular example of a mesoscale system that we're particularly interested in here in Singapore is a Sumatra squall. So the radar animation on the left is showing a recent example of one of these. So you get these huge kind of bow echo shapes. These propagate eastwards across Singapore, typically in the early morning, bringing intense precipitation, thunder and lightning, strong wind gusts. They often wake us up early in the morning in Singapore. The reason they tend to occur early in the morning is because they're tied to the diurnal cycle over Sumatra, specifically the convection over Bukit Barisan along that west coast of Sumatra, and also in the Strait of Malacca, where these systems tend to kind of organize and strengthen. And they also have a seasonal cycle, sorry, they can occur most of the year, but they won't tend to happen very much in DJF because we're then in the wrong phase of the monsoon, the winds are blowing the other way. And so we can also see how these Sumatra squalls are affected by the large-scale drivers. So here we have composite anomalies are associated with the MJO at the top, and then the Kelvin wave, Rossby wave, and the mixed Rossby gravity wave at the bottom. So these composites have been produced firstly by finding the anomalies associated with each of these large-scale drivers, which has been done through wave number frequency filtering. So if you're familiar with the Wheeler and Collardis paper, then you'll know that you can pick out a certain section of the wave number frequency space and use that to filter the OLR and the wind field, and you get the anomalies associated with these drivers. And then this paper, which is by Han Nguyen from the Bureau of Meteorology, which we here in Singapore worked on with her, She took composites over all the days when a Sumatra squall made landfall over Singapore. And you can see that this tends to occur when the MJO has its active envelope kind of over the maritime continent. This is roughly speaking sort of phase 5. When you've got the westerly wind phase of an equatorial Kelvin wave, when you've got the cyclonic phase of an equatorial Rossby wave. The MRG waves, the signal is much weaker. She's had to multiply all the anomalies by 3 here on the plot, so actually it doesn't have such a strong effect. So you can see that we're starting to build a picture here of ways in which the MJO and also these other drivers, the equatorial waves, actually modulate the amount of rainfall that we get. How that actually happens in practice. So everything I've shown so far has basically been kind of diagnosing scale interactions using composites from observations. As I say, I've talked about the MJO and equatorial waves here. There are lots of other drivers I could be talking about as well. But what we haven't really looked at still is the actual physical mechanisms of these scale interactions. So what is it, for example, that changes during each phase of the MJO, and how does that actually physically affect what's going on the local scale? Or we could turn that question around and say, what local variability do we have, and how does that depend on the large scale? And these are both approaches are ones that I've used in my work. So the first paper really to look into physical mechanisms of the scale interaction with the MJO and the diurnal cycle was this study by Catherine Birch. She's at the University of Leeds, and again, I was a co-author on this study. So she used SING-V, which is the Singaporean configuration of the Met Office Unified Model, the Met-UM. So she ran this for 10 years using a nested suite. So the entire domain of this map here is the 12-kilometer grid that she ran, with convection being parameterized, and nested inside that, the solid box is showing a 4.5-kilometer grid, which she ran with explicit convection. So we had 10 DJFs that we could analyze, so 900 days. And of those, around 600 days had an MJO of amplitude of at least 1. And so then the 2 rows of figures here are showing the daily mean precip anomalies for each MJO phase, with trim rainfall along the top row for the 10 years that she ran, and the model along the bottom. And so you can see there are some model biases, but broadly speaking, the model is doing something sensible. The wettest phase is around sort of phase 3 into phase 4. The drier phase is kind of 6 and 7. So we were sort of satisfied that we have something realistic looking that we could use. And then I'm skipping ahead to the key conclusions of this paper. So this schematic diagram lays out what we found. So here we've got picked out 4 of the MJO phases, 1, 3, 4, and 6. And then this schematic diagram is showing a slice through Sumatra. So here's the mountains on the west side. So to the left on this diagram is to the southwest, to the right is to the northeast. And so you can see in the pre-active phases and the active phases of the MJO, so these kind of first 3 that are shown here, you've got on the large scale this moisture flux convergence into the region. So we know that that's going to give us broadly wetter conditions, and then the moisture flux divergence in the later suppressed phases. If you look at what's happening at a local scale, phase 1, you can see that because we've got on the large scale broadly clearer skies, that means we've got stronger surface fluxes. So you can see the short wave down here is a much larger arrow than we see in other phases. This means that you get stronger heating of the land. It means that you get a stronger land-sea temperature contrast. It means, therefore, that you get stronger sea breezes blowing on shore. So these solid black arrows here are showing the stronger sea breeze as opposed to the weaker sea breeze that we'll see later. So you've got warmer surface, you've got more convergence over the land, as well as moisture flux convergence in the area. And so this all combines to support the diurnal convection, the diurnal cycle being triggered. And even though we are ahead of the main MJO envelope, which is still over the Indian Ocean, or out of picture here. When we move through to, say, phase 4, so now we're in the point where we've got the active MJO over us, but you can see you're starting to get the more suppressed conditions over the land. So you can see the oranges over Sumatra there. So even though we've still got the moisture flux convergence into the region, because in the large scale you've now got more rainfall, you tend to get lower surface fluxes, and therefore not so much heating of the land, not so much of a land sea temperature contrast, weaker onshore flow, weaker convergence. And so all of these things mean that you're less likely to get the diurnal convection triggering. And so you get fewer days with that diurnal convection. So that's why you then get the suppressed anomaly starting to appear over the land. When you get into phase 6, yes, we've got clear skies, so you've got the stronger surface heating and the stronger land sea temperature contrast and the stronger sea breezes and stronger convergence and everything again. But now we're into a time when you've got strong moisture flux divergence, so then you just don't get the diurnal convection triggering again. So that was one study that looked into kind of the physical processes controlling this the scale interaction between the MJO and the diurnal cycle. Another study, which I did, was using some observations. So this was using the 2 field campaigns that happened at Bengkulu, and just off the coast of Bengkulu, there was the research vessel, the Mirai, Japanese vessel. So there were 2 field campaigns, one in late 2015, the so-called pre-YMC campaign, and then the YMC campaign in late 2017 and into 2018. So for this study, I was thinking about, again, so what is it that, what kind of variables are there that actually control the local scale diurnal cycle? And we'd already seen from Catherine's work that the local sort of land sea breeze seemed to be important. So I was thinking a lot about the coastal winds. So Bengkulu is right on the coast. So taking radiosondes from Bengkulu, which were launched every 3 hours during those campaigns, I took diurnal cycles of the vertical profile of zonal wind, and using a clustering algorithm, k-means algorithm, I clustered those into 3 different clusters. And these are shown on the top panel here. So the x-axis, which is labeled down here, is local time, y-axis is pressure. And so then I've got 3 different clusters of diurnal cycle. Cluster 0, where I've got strong onshore winds. Cluster 1, where I have moderate onshore winds, and then cluster 2 is mostly offshore winds. So in fact, if you subtract the daily mean from each of these, you get the diurnal anomaly, which you see on the bottom row. So you can see in all cases, in an anomaly sense, you get a sort of a change in wind direction, so a land sea breeze circulation, even if in the total field, the wind is always blowing one way, because you've got this strong daily mean that adds onto it. Now, why is it useful to cluster the coastal winds like this? Well, it turns out that these also define different regimes of the precipitation. So now I have Hofmöller diagrams taken over this red box. So the long edge of the red box here is the x-axis on these diagrams, and I've got time going downwards. The green spike below is showing the orography of Sumatra. So if you look at cluster 2 on the right, which is where we had offshore wind, this is where we get the classic diurnal cycle, so intense precipitation over the mountains in the afternoon and evening, and then propagating offshore to the southwest. Whereas if you move to cluster 0, there is some diurnal cycle visible over the land, but it's very weak, and you certainly don't get the really intense convection being triggered in the afternoon and evening. And over the sea, it's mainly just sort of large-scale rainfall dominating everywhere. Cluster 1 is more like a sort of combination of the 2. So it looks like the coastal winds are controlling what local precipitation behavior you get, what diurnal cycle behavior you get, what offshore propagation behavior you get. So then the question is, what is actually controlling those coastal winds in the first place? So by using a regression technique, I attributed anomalies in the U850 at Bengkulu to various large-scale drivers. And what I've plotted here is time series of U850 for the periods of those 2 field campaigns, the 2015 one and the 2017 one. So if you look at, firstly, the thin black curve, which is this one here, that's just the mean seasonal cycle of the U850 at Bengkulu. The green one, which is only changing very, very slowly, is a contribution from ENSO. In the blue is the contribution due to the MJO. And then all of the other colors are contributions from equatorial waves. So the Kelvin wave, then we've got the n=1 Rossby and n=2 Rossby waves, and the westward mixed Rossby gravity wave. If you take the sum of all of these colored curves, including the seasonal cycle, you get the thick black one. Okay, and then the thick gray curve is just the full field from the reanalysis. So if all of these contributions to the wind that I'm showing here, if those were the only things in the picture, then the black and gray curves would perfectly line up with each other. And you can see that to a pretty good extent, they do line up with each other fairly well. So these large-scale drivers are the major things that are contributing what these coastal winds look like. And then down the right-hand side, I've also shown which of those three clusters we were in. So red 0 is the strong onshore wind cluster without much of a diurnal cycle. And then the blue 2 is the offshore wind with the strong diurnal cycle. And you can see examples of how each of these large-scale drivers can affect which cluster we're in. So just to pick out some examples here, there were these 2 days when we shifted from offshore wind to onshore wind, and it suppressed the diurnal cycle to some extent. And you can see hidden behind the grey curve, there's a dark pink curve. So you can see that sort of equatorial Rossby wave, which came through the region. So that equatorial Rossby wave, through its control on the coastal winds, suppressed the diurnal cycle for a couple of days. Down here, you can see the MJO. So an MJO event came through. And again, this pushed us into a strong onshore regime. So this is where we just had large-scale rainfall and not much of a diurnal cycle. There's also the stars that I've drawn here when a tropical cyclone was nearby. So I haven't tried to do any kind of attribution with the tropical cyclones, but you can see here's an example where the black and grey curve didn't really line up very much, but that was probably because of the TC in the region. And so having seen all of that, we would expect these clusters then to correlate with the different phases of the large-scale drivers. So for the purposes of this, rather than just using the 2 field campaigns, I extended this to 41 DJFs using the reanalysis and redid the whole analysis that I'd done. So this time I ended up with 4 clusters out of the k-means clustering rather than 3, but the same principle applies. They still have this relationship with the diurnal cycle. So clusters A, B, C, and D, I'm now calling them. So cluster A is when you get the weaker diurnal cycle. Cluster D is the stronger diurnal cycle. So you can see that when you have the stronger diurnal cycle and more offshore propagation to the southwest of Sumatra, that's more likely to happen when you're in an El Nino phase, whereas the weaker diurnal cycle is more likely to be with La Nina. So La Nina tends to suppress the diurnal cycle there. And with the MJO, we see kind of what we expect. This is the vanguard effect again. So grey here is showing days without an MJO, and the colours are showing the various MJO phases. So when you have the stronger diurnal cycle, that tends to be phases of 8 to 3, so kind of pre-MJO and as the MJO is just arriving, whereas the suppressed ones up the top tend to be once the MJO has arrived or is moving out towards the Pacific, so phases 4 to 6. So the suppressed anomalies are leaping ahead of the next suppressed envelope that's coming along behind it. So what I then did was actually quantify the contributions of these large-scale drivers to the variability in the coastal winds and looked at which are the main large-scale drivers that have an effect that give you the strong onshore regime and the strong offshore regime. So the strong onshore regimes, that's when you have the just kind of large-scale rainfall and you can get some kind of propagation onshore occurring. That's most likely to happen during MJO phases 4 to 6, during a La Nina event, or when you have a Rossby wave in the cyclonic phase. Whereas the offshore wind regime, that's when you get the intense diurnal cycle triggering over the mountains and the offshore propagation. It's most likely to happen during MJO phases 8 to 3, during an El Nino event, or during the cyclonic phase of an equatorial Rossby wave. One caveat here is people always ask, why didn't Kelvin waves come out as one of the most important drivers? And people are absolutely right to ask that. It's something that retrospectively, after publishing this paper, I wish I'd actually gone back and looked at a bit more carefully, I think there may have been an issue with the analysis and the way I attributed the wind to the Kelvin waves. I suspect there may have been an issue in there. So from elsewhere in the literature, you would definitely get Kelvin waves also being an important driver here. Now, I ran the same analysis for other coastlines as well. So the coastlines where you typically get offshore propagation occurring. So for Northwest Borneo, you can see that, again, the MJO and the Rossby waves came out as important. For propagation to the north and south of Java, it was the Rossby waves and the WMRG waves that were important. And for propagation north and south of New Guinea, it was the WMRG waves, and then specifically the N=2 Rossby waves, which turned out to be the crucial ones. So that's looking a bit more into the physical processes of how the large-scale drivers control the local winds, and that the local winds seem to have a control on the rainfall. And we've seen that the offshore propagation of the convection is an important feature of all of this. But what I haven't done yet is looked at the physical mechanisms of that offshore propagation itself. So that's what I looked at in my next paper, which was published in 2023. So here, I've taken, again, a Hofmöller diagram over a similar area, focused on Bencoolen. So this is all from GPM iMerge observations. So here we have, again, Hofmöllers with the x-axis being the long edge of this red box, and time going downwards. And so you can see, if you take a composite diurnal cycle, I think this is over DJF, you can see that you get the intense convection over the mountains in the afternoon and evening and propagates offshore. But we know that actually this convection doesn't happen every day. So if you just pick out days that actually have the offshore propagation happening, you get a far clearer picture. And in fact, you can see that in the offshore propagation, you can see I've drawn a kind of range of phase lines on here. You can see that you appear to get a range of propagation speeds. So sometimes you get this happening at much slower speeds, something like 3 meters per second, sometimes much faster speeds, sort of 15 meters per second. So the question is, what causes the convection to propagate, but also what causes it to propagate with such a range of speeds? Now, if you look in the existing literature, you'll see there's various suggested physical mechanisms as to why this offshore propagation occurs. So it could be due to gravity waves. So gravity waves are triggered, and as they propagate along, they trigger further convection. And various studies have suggested why this is. It could be the convection itself actually triggering gravity waves. Could be gravity waves triggered by the nighttime radiative cooling over the land, or triggered by the evaporative cooling from the rainfall. Another kind of family of proposed mechanisms is that it's due to convergence, due to density currents, where you have density currents propagating in the boundary layer and converging with environmental winds. That gives you low-level convergence, and that triggers further convection as it goes. And it could be that these density currents are cold pools from the convection, or the land breeze moving offshore. Or this propagation could just be advection. So it could be just that the convective clouds are themselves being advected along by some steering flow. Or it could be that the anvils of the convection are advected by the upper level winds, and then you get the feeder mechanism where those anvils then seed mid-level clouds beneath them, and that then enhances the precipitation kind of further and further offshore. So just speaking kind of anecdotally, I find people often kind of assume it's gravity waves that are responsible for the propagation, but actually we see there's this range of things in the literature. So I wanted to investigate these mechanisms in a convection permitting model. So I picked out 3 case studies from the pre-YMC campaign when we knew that we had strong offshore propagation. I ran the MET-UM on a 2.2 kilometer grid over this gray box here, using a convection permitting setup. And here I've shown maps of precipitation for those 3 different case studies. So each row here is a separate case study. So the 25th of November, 30th of November, and 3rd of December. The 4 columns here are showing 4 different times. So 3 p.m. local time, 9 p.m., 1 a.m., and 5 a.m. And the blue colored shading is showing precipitation. So you can see at 3 p.m. in all of these cases, we've got the precipitation starting to form kind of over the mountains. So this is the classic diurnal cycle. And then in the subsequent plots, you can always see that precipitation propagating offshore. The brown contours that I've drawn on here are the gradient of low-level theta V, so that's virtual potential temperature. And where you see those brown contours, that is really showing the front of a density current. So the air inside and outside of the density current have very different theta V. So at the front of that density current, there's a sharp gradient. And so you can see this picks out very well things like cold pools. So you can see sort of everywhere where you've got precipitation, you tend to have a brown contour around it. So that's the cold pool coming out from the rainfall. But you can also see, and this is where I've drawn on just subjectively, the orange shapes here, it picks out the land breeze kind of moving offshore. And you can see that broadly speaking, the precipitation is kind of in line with where that land breeze is. So it looks like the precipitation coming offshore is propagating kind of in time with the low level density current front that's caused by the land breeze propagating offshore. So to look into this more, here are some vertical cross sections. So just to talk you through what's shown on here, so this is the green is the mountains of Sumatra. To the left is going southwest offshore. The vectors here are showing the wind kind of in that plane. So anything pointing to the right here is blowing onshore. And the colored shading is showing that as well. So purples and blues are onshore wind, oranges and reds are offshore wind. The gray contours are showing the cloud concentration. And the black contours are showing theta V, which I've just plotted up as high as 305 Kelvin. So that's roughly speaking showing the boundary layer. So you can see here the boundary layer is pretty well mixed, as we expect. So these 2 times I'm showing midday local time and 4 p.m. local time, just for one of the case studies. So you can see that around midday, you've got this sea breeze blowing onshore in the orange. You've got upslope winds, you've got some convergence over the mountains and some clouds starting to form. By 4 p.m. that has deepened, so we've now got deep convection, we've got intense deep clouds, and the blue curve on the bottom panel here is showing the precipitation that's now falling over the mountains. And you've got this very much strengthened sea breeze that has grown throughout the day. As we move on, so now at 8 p.m. local time, you can see that deep convection is still precipitating, but you can see it's now shifted towards the coast. And you can see over the slopes here of the mountains, you've got these extra black contours and a little bit of blue that's showing offshore flow. So this is a katabatic flow that's formed and is now blowing down the slopes. And you can see that's forming convergence just here around the coastline. And the red curve on this lower plot is showing moisture flux convergence. So you can see that the convection has propagated in sync with that low-level convergence due to that katabatic flow down the mountains. That katabatic flow is then what turns into the land breeze and propagates offshore as a density current. And so you can see now it's shifted slightly further offshore, and the precipitation is still in sync with that moisture flux convergence due to that density current front. And as we go through the night, the density current flows further and further offshore. And although the picture kind of gets messier as the night goes on, you can still see, broadly speaking, you've got the precipitation coinciding with the moisture flux convergence as that propagates offshore. Now, I mentioned that the literature also refers to gravity waves. So as well as, even though we seem to be showing here that the propagation of the convection is because of the convergence caused by those low-level density currents, I also wanted to see, is there any role for the gravity waves? So if you look at the second panel here, this is another Hofmöller diagram. Again, the x-axis is the same as before. So to the right is over the land, to the left is over the sea. Time is going downwards. And this is column averaged vertical velocity, W, so averaged over the whole height of the troposphere. And you can see the bright colors here are the deep convection, so forming over the land and then propagating offshore. But you can also see you've got some faster propagating signals in the darker purples. So what I did was to use a high-pass filter to remove anything with a period of more than 1 hour. So anything that evolves more slowly than timescales of an hour. So I removed basically this deep convection. And so that's what you get in panel C here. So I've now added black contours, which are the precipitation. But you can now see more clearly in the dark purples, these faster features. And I've drawn on in the yellow lines the theoretical phase speed of gravity waves, having calculated the static stability from the model. And so you can see that these features propagate along with the speed of, roughly speaking, an n=3 gravity wave. And this was just for one of the case studies. Panel A and panel D are showing the other 2 case studies, and you get a similar picture in those 2. So it looks like we are getting gravity waves in the model. So again, the panel A here is a Hofmüller diagram with the colored shading being the vertical velocity again. This time I've just picked out one particular altitude, 2 kilometers, for one of the case studies. The black contours are the precipitation. So again, you see that propagating very slowly. What I've also drawn here is a yellow dashed line along the trajectory of one of these faster features, which is a gravity wave. And just to convince ourselves that it really is a gravity wave, I've zoomed in on this yellow box. That's the panel on the right. And so here I've shown again the W, vertical velocity, and the colored shading. And the black contours this time are showing theta. And you can see, if you look carefully, the W and the theta are in quadrature with each other. So the theta here, for example, is peaking just between the red and the blue at the vertical velocity, exactly as we would expect for a gravity wave oscillation. So if you look back at these kind of gravity wave speeds, you can see I've drawn these yellow stars on here. Each of these yellow stars is at a location in the plot where you get some precipitation just forming. It's only the thin black line, so it's very weak precipitation, but you do get precipitation sort of being triggered, apparently by these gravity waves. Most of it is not very intense. So the intense, organized line of convection is still the thing that's propagating very slowly with the density current. But there does seem to be a role for these gravity waves. And sometimes, this example here, you can see the convection does actually deepen and intensify. And so you get quite intense precipitation. But it's still quite isolated. If you were to look at a map, it would not be an organized line. These are still kind of isolated bits of convection. But they occur along this gravity wave trajectory. So if we go back to the Hofmüller diagram we saw earlier, this is a composite, remember, the slower propagation speed, sort of 3 to 6 meters per second, say, that's organized convection that is propagating along with the density current due to the low-level convergence. The faster speeds are along gravity wave speeds. And this isn't really propagation in a meaningful sense. If you were to look at an individual day, you would just see kind of bits of individual rainfall. But when you average over everything in a composite, that kind of smooths out in the averaging, and you get what looks like kind of faster propagation speed, sort of apparent propagation speed. So just to summarize the results of that study. So on days where you get the diurnal cycle and the offshore propagation, midday you're getting a sea breeze and convergence over the mountains, clouds starting to form. That begins to precipitate throughout the afternoon and deepen into deep convection. That can fire off gravity waves. You then get this katabatic flow down the mountain, which turns into the land breeze. So the cold front symbol that I've drawn on here is the front of that density current that's propagating, and that gives you low-level convergence with what is sort of left over of the sea breeze. And so this cloud here is a cut through an organized squall line that's propagating slowly offshore. The gravity waves can themselves trigger bits of isolated convection, some of which deepen and intensify, but it really is just isolated, not properly propagating. So that's all done in a model. There's then a question of, can we verify any of this using observations? So the reason I looked at the offshore propagation to the southwest of Sumatra is because of that field campaign where the Mirai was stationed about 50 kilometers offshore. And so now I'm plotting here time series from the AWS on the ship. So the red here is showing the onshore wind. The black is showing theta V, and precipitation is shown in blue. The bottom right here is the only panel that's come from the model. So that's the case study that I was plotting in the vertical profiles. So you can see that when the land breeze comes through, it's actually not so clear in the model as it is in the observations. When the land breeze comes through, you get a change in wind direction, going from positive to negative here. You get a sudden decrease in the theta V, and it's around that time that you get the precipitation. In fact, in the model, it doesn't look quite so good. The model actually has it slightly preceding. But if you look at the observations, it's much clearer, actually. So you get cases with a very sudden wind direction change, a very sudden drop in theta V, and it is typically either right in time with that or just after that that you get the precipitation. So it does indeed seem as though the precipitation that's propagating offshore and comes through over the ship is happening in time with that density current coming through. So that was looking at cases where we know that the offshore propagation was happening and thinking what was the physical mechanism. What I'm also interested in is why you get variability. We know that this diurnal cycle doesn't trigger every day. We know that the offshore propagation doesn't happen every day. So what's controlling that? So this was a paper that I published earlier this year. So to look into this, I took, again, Hofmüller diagrams, very much like the ones we've been looking at throughout this talk, this time from observations, so from GPMI merge. I used 10 DJF, so I had 900 days, and 2 of us subjectively classified all 900 of those images into 4 different regimes. It was a very tedious task, but we got through it. So I defined sort of by eye these 4 different regimes, which are days where you get a diurnal cycle, so triggering here, but no offshore propagation. Notice you can get the onshore propagation, but I wasn't looking at that in this study. Days with the diurnal cycle where it does propagate offshore. Days where there isn't much of a diurnal cycle, it's just dominated by large-scale rainfall, and days where there's little or no rainfall at all. And so then these are histograms of how frequently you get each of these 4 regimes occurring by a large-scale driver. So you see that there is an influence from the Indian Ocean dipole and from ENSO. And you can also see the vanguard effect going on here. So in sort of phase 2, sort of pre-MJO, is when you're getting the peak in the diurnal cycle and the diurnal cycle occurring. And when you get into the active phases of 4 and 5, that's when you just move into the large scale without much of a diurnal cycle. So the diurnal cycle was strongest just ahead of the active MJO. But do notice that for all of these drivers, you can still get any of these regimes happening in any phase of any driver. So when we talk about the scale interaction between the MJO and the diurnal cycle, it doesn't mean that if you know the MJO phase, then that uniquely defines what's going to be happening on the local scale. There's still variability within that. So what actually is controlling the variability? So again, for this, we used a modeling study. So this came out of the Terra Maris project. So Emma Howard, who is now at the Bureau, but at the time was at the University of Reading, ran this set of simulations over the whole of the maritime continent. So for 10 DJFs, she ran this setup with a 12-kilometer grid shown in blue here. And then that was forced with ERA 5, and then nested inside that a 2-kilometer grid that had explicit convection. And these are run for the same 10 DJFs that I was using for the analysis on the last slide. So having done all of the classification into those 4 regimes using the observations and done all of that subjectively, I was then able to speed things up and automate the process because I needed to do those classifications again in the model. So using the observation data set that I'd done subjectively as a training data set, I was able to get a convolutional neural network to classify all 900 days in the model. And then let's look at the dynamical conditions associated with each of those days. So here is the 10-meter winds shown in the vectors, and the convergence of that 10-meter wind field shown in the colored shading. The black contours are precipitation, and this is for each of those 4 regimes. So you can see the 2 on the left, which have a diurnal cycle, look pretty similar. So you've got an onshore component of the flow. That means you've got more convergence in the blue, and you can see in the black contours the precipitation forming over the mountains. But notice there's really not much difference between these 2 plots. So this is a 1 p.m. local time. So at this stage, there's not much difference between these 2 in terms of whether the propagation happens. But when you don't get the diurnal cycle, you tend to have the winds just blowing along shore, not much of an onshore component. Any convergence you get is weaker. And you can see in this large scale case, the precip mainly kind of forming over the sea, and then very little precip in the none case. So that's the dynamical situation. We can also look into the thermodynamics. So I've plotted here the moist instability in each of these 4 cases, 7 a.m. local time on the top row and 1 p.m. local time on the bottom row. So to plot moist instability, I've used quite a simple metric here. So this is theta E at a low level in the boundary layer, so 300 meters, and subtracted the saturation theta E at a mid-level, so 4,500 meters. So if you think of an air parcel starting in the boundary layer with some amount of theta E, it ascends to mid-levels, by which point it's bound to be saturated. The question is it still positively buoyant when it gets there? So if this thing is positive, which is shown in blue, then you have moist instability. So at 7 a.m., no matter what regime we're in, over the mountains of Sumatra, we have an atmospheric column that is stable against convection. But by the time you get to the middle of the day, in these 2 diurnal cycle cases, we've mostly got instability that's built up, and that explains why the diurnal cycle triggers, whereas in these other 2 cases, it remains stable. So what is then controlling this moist instability? So I've now plotted that same metric again, but this time I've taken an area average over all of the land that's above 500 meters, so basically over the mountains. And the colored curves are each of the 4 regimes. So the blue and yellow curves are the 2 diurnal cycle ones. So this confirms that in those 2 cases, you do indeed get the instability, whereas in the other 2 cases, it remains stable all day. So this is a mean diurnal cycle. So this is kind of afternoon time is when you get most of the instability. If you plot the 2 terms in this metric separately, you see that it's the low-level theta E that has the larger diurnal cycle and the larger differences between the regimes. So it's the low-level boundary layer thermodynamics that are controlling the diurnal cycle behavior. It's not what's going on at mid-levels that's exerting much of a control. Okay, so what is it then that's controlling this low-level theta E? Okay, so theta E is a function of just equivalent temperature and pressure. The pressure variations I haven't shown here, but they're negligible. So we can just think about equivalent temperature itself. So what's controlling the equivalent temperature? Well, equivalent temperature is just the sum of the dry bulb temperature and this moisture term. So that's the warming due to precipitating out all of the moisture in the air parcel. And you can see that if you just plot the dry bulb temperature, again, you get a very small diurnal cycle, very small differences between the regimes. Whereas when you add in the moisture term, that's when you get in the variability. So it's actually the low-level moisture, so the boundary layer moisture availability, that is really controlling that moist instability. And that is the big forcing on whether you get the diurnal cycle or not. But what controls whether you get the offshore propagation? So let's just compare now these 2 diurnal cycle regimes, the one that doesn't propagate and the one that does propagate. And there's a few different ingredients kind of in the story here. So one is the mid-level flow. So this is now at 5 p.m. Local time, the 500 hectopascal winds. You can see that in the case without propagation, you've got the winds blowing broadly onshore, whereas in the with propagation case, you've got them broadly blowing offshore. So this could be providing a steering flow. But I was also interested, thinking again about instability, how the instability changes in these two cases. So if you think of a storm that's propagating along, it's propagating through an environment where you've also got some background wind. So if the storm were propagating along at exactly the same speed and direction as the wind, then no air would be entering the convective plume as it moves along. However, if it's moving faster or slower than the environmental wind, the convective plume as it moves along will either be kind of catching up with the environmental air and so ingesting air that's ahead of it, or if the wind from behind is faster, then the air from behind is kind of catching up with the convective plume as it moves along. And again, you've got air being kind of ingested from behind. And the question is, does that air that's being ingested into the system add any further instability? So there was a metric devised to look into this in this paper, Alfaro, in 2017. So he devised what he called layer lifting CAPE. So you take the difference between the environmental wind, U, and the propagation speed, PS, and you weight that by CAPE as a function of P. So that means the CAPE that would arise if you did a CAPE calculation having lifted an air parcel from pressure level P. So if an air parcel enters the storm at pressure level P, what CAPE is then added? And we do this integral over the whole of the troposphere. And if you do that for the two different cases, bearing in mind they have different thermodynamic profiles, you get quite different results. So in the mean diurnal cycle, you see that in the propagating case, this adds quite a large amount of instability, which is going to be supporting further convection as the storm propagates along. Whereas if you take the vertical profiles from the no propagation case, we can calculate that if you did have a storm propagating, the amount of instability that would be added as it propagates is much less. So on these propagating days, the local thermodynamics are actually liable to add more instability than on a no propagation day, which then supports the convection continuing to be strong as it propagates along. And I haven't shown it here, but the thing that exerts the biggest control on this kind of difference between these two curves, again, turns out to be the low-level moisture. So the low-level humidity is really important here. So just a schematic diagram kind of summarizing that. So on days where you get a diurnal cycle, whether or not you get the propagation later, in the early afternoon, we've got onshore flow, and we've got low-level humidity. This causes moist instability, and you get the deep convection. Whereas in the large-scale case, you've just got a longshore flow, so that's coming out of the screen, and a stable column over the mountains. And so although you've got large-scale rainfall, you don't get the diurnal cycle triggering. And then you get the days with no rain. Again, just the winds tend to be alongshore, and you get a stable atmosphere. As we move into the evening, that's when we then see the difference between the two diurnal cycle cases, one with propagation and one without. And that's partly due to a difference in the mid-level flow, which can act as a steering flow, and partly due to this low-level humidity, which means we can ingest more instability into the storm as it propagates along. So that kind of finishes really most of the science I wanted to talk about. I know there's now a Q&A session, so I've got just a small handful of slides which I think will sort of kickstart that session. So I'll just go through these slides, and then I'll hand back to you, Yudo, when I've gone through these slides. So one thing that I want to think about now, I work at the Met Service Singapore. Obviously, we're an operational forecast center as well as having our research center at CCRS. So we're not just thinking about the fundamental science now, we also want to think about how we can translate this into something that's impactful and useful for operations. So recently at MSS, we had a workshop to start exploring this. And so this is something I'd be very keen to hear some comments on when we open this to questions. So one of the things we were looking at is there are existing tools. So there's the Carl Schreck website, and there's the MISFA website, which was developed by Météo France, which can show us the contributions from MJO and equatorial waves to the traditional fields that forecasters look at. And so they allow us to kind of build up some storylines about the large-scale flow and get forecasters thinking about how these large-scale drivers are impacting the fields that they're looking at. We also started to explore some products that could be used. So on the left-hand side here, here's an example of something I developed. So this is going back to the concept I mentioned earlier, that you can look at, say, a composite of the rainfall during a particular phase of a particular large-scale driver, but it's just an average. It doesn't actually tell you necessarily what's going to happen on each individual day, and you can still get a lot of variability within those phases. So what I'm showing here is histograms of precipitation over Singapore for each of the 4 phases that we've defined of an equatorial Kelvin wave. So you can see that when you're in the low-level convergence phase of a Kelvin wave, this is what the histogram of precip looks like. So heavily skewed towards the higher values. So the probability of getting extreme rainfall on the right is much increased when you're on a when you're in the convergent phase of a Kelvin wave. However, you can still get zero rainfall. It's not a zero probability, but the probability of that is much reduced. And then something that Sam Ferret, she's a researcher at the University of Reading, and she was one of the, we had a number of external experts who helped us with this workshop, and she was one of them. She's done some work looking at the impact of equatorial waves, and particularly recently looking at the impact of combinations of equatorial waves. So this is showing for Peninsular Malaysia, the probability or the change in probability of getting a rainfall extreme in various phases of waves. So I think she was looking at rainfall above the 95th percentile. So we have on the x-axis a Kelvin wave, and on the y-axis a westward mixed Rossby gravity wave. So if you look here in the convergent phase of a Kelvin wave, if you firstly disregard the WMRG wave, this is saying that the probability of getting extreme rainfall is more than doubled when you're in the convergent phase of a Kelvin wave. But she also found that if you have the convergent phase of a Kelvin wave and the positive vorticity phase of a WMRG wave, and that happens on average, I think, about once per DJF, you're more than 8 times as likely to get extreme rainfall. So this is the kind of product that we feel might be useful for forecasters, that's really kind of summarizing the impact of these waves. So just to summarize what I've been talking about in this talk, so we've seen that the spatial and temporal variability of convection in the maritime continent are controlled by the land sea temperature contrast. You get very complex coastlines and complex orography, which give rise to this diurnal cycle in the region. But also it's important to look at the scale interactions between the large scale and the local scale. So we've seen that the MJO has a major control on the large scale environment, and that the diurnal cycle peaks ahead of the active MJO envelope. And this has become known as the vanguard effect, where over land, that diurnal cycle is strong enough that the MJO anomalies themselves leap ahead. And we've looked at large-scale processes that then affect the diurnal convection through changes in surface fluxes, land sea breezes, boundary layer humidity, and so on. And understanding these processes by the large-scale drivers is key to understanding why these scale interactions occur. So a lot of what I've shown in this talk has been from models when it comes to the physical processes. Catherine Birch's paper that I showed earlier was the first paper that looked into why these scale interactions happen at process level, and I've continued to look into that. But as I say, there's not a huge amount of verification that's gone on. And so one of the challenges of the maritime continent is that there aren't many observations compared to other parts of the world. Where we do have observations, it tends to be things like the YMC field campaign, so you have an intensive observation period, but not necessarily such long-term data sets. So the YMC was successful in leading to some field campaigns. I was involved in the UK's contribution, Terra Maris, which unfortunately didn't happen because of COVID. We didn't have the field campaign aspect. So overall, I would say quite a lot of our understanding of these scale interactions at the physical process level remains theoretical, because a lot of it does come from modeling, not observations. So I'd like to sort of pose the question of where we go from here, really. So there are a handful of studies using in situ observations, and I've listed a few here. But we really need more of these, I think, and we need greater kind of availability of data to be looking into this. Another thing I'm going to throw into the mix here, just a thought, is I wonder whether our understanding of the MJO is actually sufficient to be able to do this scale interactions work well. There's lots of theories of how the MJO propagates. All these theories have weaknesses. We don't really understand how the MJO propagates. So this is more just a thought which people might like to comment on is, do we actually need a better understanding of MJO propagation if we're to have a deeper understanding of these physical processes of these scale interactions? And as I alluded to when talking about the recent workshop we had at MSS, there's a question of how we translate our knowledge of scale interactions into information that is useful for forecasters. So how do we deliver impact through our understanding of the local scale response to the large scale? And just to finish, I'm going to flag up a couple of conference sessions. So I'm not involved in organizing, I'm not involved in convening these sessions, but just to say at the AMS Hurricanes and Tropical Meteorology Conference next year in San Diego, there will be a maritime continent session. There hasn't always been a maritime continent session at that conference. And there's also been talk of having perhaps a post-YMC session at AOGS next year, which is in Fukuoka in Japan. And that would be an opportunity, if it happens, to discuss the future of maritime continent research. So the first of these, the San Diego conference, abstract submission is now open if you fancy traveling to America. And so just to finish, if you're interested in my papers, you can scan that QR code and that takes you to my Google Scholar page. Yeah, thank you very much. Back to you, Yuda.
Thank you, Simon. Okay, so it's covered a lot of grounds. Multi-scale interaction of convective system in our region. Now we go to Q&A session. We have about less than 45 minutes until 11 a.m. here in Bandung. And maybe I will start with the question from myself. Just a little bit overview of all the explanation about the convective system that you just presented here. So the structure of the large-scale system, the MJO, as you said, the vanguard effect, is driven or contributed by these by the diurnal cycles. But then the dynamics of the diurnal cycle itself is driven by the large-scale system. So there's this interaction, which makes quite a complex perspective. How, I mean, sometimes I believe that can be some simple explanation, but it may not. Can I have what your view on this?
Yeah, so you definitely have to think of scale interactions as being two-way. And you're right, that makes it complicated. So I think, and I have looked at it in both directions. So I think the large scale drivers, so that could be MJO, but it could be equatorial waves, and it could be all the other things, you know, ENSO, IOD, and so on, monsoon flow. They provide the dynamical and thermodynamical conditions in which the diurnal cycle occurs. So whether you get the diurnal cycle triggering or whether you get convective propagation occurring and so on, as I was talking about from my most recent paper, that depends on the environment that is set by the large scale. I think that is the best way to think about it. However, the trap that you fall into, if I go right back to the beginning, is, as I mentioned earlier, you look at something like this, you know, map of an MJO composite, and you fall into the trap of thinking that what you see in each of these panels is what happens in MJO phase 1. Like MJO phase 1 would always look like this. MJO phase 2 would always look like this. And of course it doesn't. That's just the mean of a much broader distribution. And so there's a lot of variability within those phases. And so that is why it is also helpful to look at it the other way around. So rather than just doing a composite of the large scale and saying, what does the local scale look like then? Because that hides a lot of the variability. You can also look at it the other way, start at the local scale and say, okay, if you have a day with a diurnal cycle triggering or a day without a diurnal cycle triggering, whatever, what is the cause? And so that really was the thinking behind this paper, where you, rather than a large scale to local scale view, you flip it round and you take a local scale to large scale view. So you begin with what's happening at local scale, and then you ask what large scale conditions are kind of setting that. Kind of whichever way around you do it, I think you can't really escape having to form a composite. You either have a composite view of the large scale and then ask what happens on the local scale, and that kind of hides some of the variability, or you take a composite view of local scale events and ask what was the large scale, and again that kind of hides some variability. So I think to come back to your point, I think you have to think of these things as two-way interactions. You have to look at them from both directions in order to get the complete picture. And I agree that that does make it complicated, but I think that is the way forwards. It possibly depends on your, exactly what you're trying to think about. So coming on to what I was saying at the end about what are the implications for forecasters and how do we translate this knowledge into forecasting? Forecasters are generally interested in what's happening at the local scale. So for them, I guess the point is you start at the local scale. And so that was kind of the thinking behind putting together diagrams like this, was that if you're a forecaster who's interested in this part of the world, basically what are the large scale drivers that you need to look out for? What I can't necessarily say is, what the large scale picture will look like on any individual day. But what I can say is what are the large scale drivers that you need to be aware of to build up a storyline that might tell us something about what the local scale conditions are that we can expect. So it's very much, scale interactions are two-way, and kind of which way you look, from the large scale to the local or the local scale to the large, does kind of depend on what science question you're asking, I think.
All right. Yeah. So the local perspective is very important to give some details, pictures, and even connected with the large scale. Okay, so we have some questions from the floor. Maybe Pak Didi, you can go ahead. Have your question. Pak Didi, go ahead.
Yes, thank you, Pak Yuda. Simon, thank you very much for the very interesting presentations. Yes, my first question is, I'm interested in the mechanisms of these scale interactions, particularly the diagram you shown us earlier on the MF moisture flux convergence on phase 1, 3, 4, 5, I think. Yes. Yes, I noticed here that in phase 3, there is quite a significant moisture flux convergence that produce more rain in phase 3 than phase 4. And my question is, what is the controlling of this moisture flux convergence? Is it the amount of moisture or the wind speed decelerations of this that cause this high moisture flux convergence? That's my first question. So my second question is regarding the offshore propagation of convections. You mentioned about 3 mechanisms like land breeze, convergence, and also gravity wave and convective outflow. My question is, what is the relative role of these mechanisms? Are they is the land breeze convergence is the dominant one, or what are the relative role, or are they interacting with each other? And I'm also interested in actually not offshore propagation, but propagation over land towards inland. Do they have like similar mechanisms with the offshore propagations?
Yeah.
Yeah, I think that's my question. Thank you, Simon.
Thank you. So coming back to your first question. So I think in the paper, I don't think we plotted different contributions to the moisture flux convergence, but I am pretty sure it's mainly controlled by the winds, because this moisture flux convergence here was calculated domain wide. So I think it is the circulation anomalies associated with the MJO. So obviously, when you're in the active MJO, you would expect zonal anomalies, kind of. So from the east, you'd have zonal wind kind of blowing into the active envelope, and from the west, you'd also have zonal winds blowing into the active envelope. So you've got kind of large scale convergence here. So I think it is mainly the circulation flow that's controlling that moisture flux convergence in each MJO phase. But as I said, I don't think that was actually plotted in the paper, but I think from memory that was the biggest control. And in terms of the offshore propagation, so I think you were thinking of this slide. So I would say what my work has suggested is that the main control on the offshore propagation is the density currents, because we clearly saw the organized convection propagating along at a slow speed, which is consistent with density currents and is really too slow for the gravity waves. We saw the low-level convergence and the density current going along in my vertical profiles. What I can't tell you is which of these two it is. So, I mean, I was referring as I was going to the land breeze. So, okay, so the land breeze is definitely important in providing this low-level convergence. However, if you look at these vertical profiles here, I mean, there could also be there. I mean, there are definitely cold pools occurring. And whether these density currents also have contributions from the cold pool, from the rainfall evaporation, well, they almost certainly do, but I wasn't able in this work to unpick kind of the two. And that's kind of future work, which is still ongoing, really, back in the UK, is to try to unpick those two and say, was it mainly due to the land breeze or mainly due to the cold pools? But I would say, of these three, what my work suggests, at least looking for this one location in the maritime continent, is it's definitely this middle one, the density currents, which have the stronger control. So I showed gravity waves kind of triggering bits of isolated convection, which then show up in a mean sense. What some other papers have shown, although I didn't look into, was there's also a role for gravity waves in that they can precondition the environment. So the gravity waves shoot off much faster than the density currents. They generate instability ahead of the density current, so that when the density current comes through, the gravity waves earlier have preconditioned the environment so that you not only have the low-level convergence from the density current, you've also got a more unstable environment because of those gravity waves that have already passed through. So that kind of is how these two work together, I guess. Then I also, in the very last bit of work, did show briefly that there may be some role of the advection. So this was where you have this, what looks like it could be a steering flow, kind of aiding the advection of these systems offshore. But as I say, mainly, I think that is due to the low-level convergence rather than the advection. You asked whether the same mechanisms occur for the inland propagation. So I personally didn't look at that. There is a PhD student at the University of Leeds who has looked at some model experiments. So he was looking specifically at Sumatra squalls, as I showed earlier, which come eastwards over Singapore. Many of those originate with the same kind of convection over the Sumatra mountains and then moving kind of northeastwards and then kind of turn eastwards as they go, kind of across the Strait of Malacca. So, I mean, what he found is that, broadly speaking, it is a similar picture. So I haven't looked into that personally, but I think, yeah, it is a similar thing. So I think in terms of Where's a good example? Yeah, so I mean, what I found is that when you have this onshore wind regime, so this is typically associated with the active MJO, and you get this kind of large-scale rainfall and some sense of onshore propagation. I think that can also be associated with convection forming more on the northeast flank of the mountain. So in my study, because I was looking at propagation going to the southwest, my propagation cases tended to have convection forming along the southwest side of the mountains. But you can also get the rainfall forming along the other side, and that tends to then propagate the other way. So that's what propagates inland and can turn into Sumatra squalls or not. And so that, yeah, that then is associated with the propagation in the other direction. And but as I say, yeah, I think the mechanism is broadly similar for that propagation.
Okay, Pak Didi, you have more question or maybe?
Yes, thank you, Simon. Actually, I have one more question. It seems like from your modeling work that the model seems to can capture these scale interactions between the diurnal cycle and MGO. So yes, I think there have been a lot of progress since previous Terra Maris proposal in 2019, I think, until now. If like you need field observations about this, what kind of observations do you think needed to confirm this kind of results?
Yeah, so for Terra Maris, for people who don't know, we were intending to have a field site on the south coast of Java here. We were going to have a field site on Christmas Island, which I think is about 400 kilometers away. We were going to have a plane that was going to fly back and forth along that transect. So we'd have had radio sondes from the two field sites and drop sondes from the plane. And so I think those would have been key, because if you get to sort of drop sondes at Curtin, be like, you've then got the vertical profiles kind of along that transect. And so I think what we would have been hoping to see is, say, the low-level convergence propagating offshore, and maybe instability as well, which kind of propagates further offshore as the system moves along. So that's one thing. I think another thing in terms of observations that we would like is, I think, greater ability to diagnose these land sea breeze circulations. So kind of coastal AWSs or AWSs on the mountains that are measuring the wind, temperature, and humidity. So if you think about the plot I showed earlier from the ship AWS, this kind of thing, this was just done for a fairly short period of time. I think if we had these low-level winds and some measure such as theta V, where you could identify density currents and timing of density currents and see how that fits in with the timing of the rainfall, I think that would be something that would allow us to verify the kind of these physical processes.
Yes, thank you, Simon.
Yeah. And then there was also, I mean, there was this one of the papers I briefly flashed up at the end. So this Geng and Katsumata paper, I mean, they looked at the low-level winds using the Doppler radar from the ship. And I think it would be interesting to look at, because I think, again, they just looked in a composite sense. It would be interesting to look at day by day, whether you can match up days with, say, a strong land breeze with getting offshore propagation, or whether actually you always get the land breeze, whether or not there's the diurnal cycle and the offshore propagation at all. So I think there's still a lot of questions we could answer if we had that sort of data.
Okay, thank you, Pak Didi. I think we give chance to other questions. There's one from the chat box. Maybe Simon, you can have a look in the chat box from Sophia Lestari. Well, Sophia, you wanna post the question directly or just read in the text here?
In the text is okay. Yeah.
Okay, yeah. So let me quickly or Simon can read himself.
Feel free to
It's
read it.
something to do with seasonal. Can you find the question?
Yeah, I have. Yeah, I've got it now. So, okay. So you mentioned that during the active MJO phases, rainfall tends to peak over the coastal areas. In suppressed phases, it's more over the lowlands. Does the season make a big difference? Okay. So the answer to that is I don't know, I'm afraid. I'm just trying to think whether I have actually looked at that by season. I think I didn't have a look at it by season. So my original Vanguard effect paper was November to April. I think I started looking at DJF, but because back then there weren't that many years of trim to look at, I extended it to November to April just to get a greater sample size. But I don't think I ever looked at boreal summer. And in the more recent studies I've done, again, I've just looked at DJF, I think. And that was partly because of when we still had hopes that the field campaign was going to happen. That was going to be in January, February. So we were just focusing on that time of year. So I'm afraid I don't have an answer for you on that. I mean, I suspect it does make some kind of a difference. The background flow from the monsoon probably changes where you would get the strongest effects going on, where within the region, but I'm speculating slightly there, I'm afraid. Since the maritime continent has very locally complex topography, pattern of rainfall peak may be different. Apart from Sumatra, have you looked at variability over other regions? Yeah, so I mean, I briefly showed this. I've tended to focus on Sumatra, again, because that's where the Japanese field campaigns were. So we had the Mirai observations. So it was kind of our only opportunity to do any kind of verification, really. But yeah, for this study, obviously, I looked at the different regions. And so you see that different large-scale drivers do make a difference, depending on where you are in the maritime continent. So one of the big differences is actually whether you're looking at propagation that's more east-west, so more zonal, or propagation that's more meridional. So it's no coincidence that the westward mixed Rossby gravity waves are more important where I was looking at Java and New Guinea. So that's where the islands are and the mountains are oriented more east-west. So, and the propagation you're looking at is more north-south. So when you're around the equator, equatorial regions, it's the meridional component of the WMRG waves that then has a big control. So that's kind of unsurprising that that driver ends up being a more important one there. In terms of the orography, yeah, I mean, I haven't really thought about the difference in orography between the different locations, to be honest. I know that the New Guinea mountains are the highest ones, and there's been a couple of studies specifically looking at New Guinea. And so when I mentioned earlier the studies into looking at gravity waves, preconditioning the environment before the convection comes through, I think in particular, that's something that's been investigated over New Guinea. So that seems to be a particularly important effect there. So I'm just going back to the chat so I can see the rest of the questions. Do you have a sense of which type of rainfall, stratiform or convective, shows up more during active versus suppressed phases? Yeah, so I think the where you get the strong diurnal cycle, that is more convective rainfall, whereas when you get the large scale regime, that is going to be suppressed, dominating more. So where were we? Yeah, so I suspect when you've got this diurnal cycle, the two diurnal cycle regimes here, I think if you did a split between the stratiform and convective rainfall, you'd have a much stronger contribution from the convective here. Whereas when you're in the large scale stuff, I mean, you shouldn't think of this as just kind of blanket rainfall everywhere. You're still going to have lots of convection and stratiform features across a range of scales, kind of embedded within this large scale rainfall, which is probably a large scale MJO envelope. But I suspect that you'd have a more even mix between convective and stratiform, as opposed to the short term, really intense precipitation, which is more the convective stuff. So yeah, in the active MJO phases, you get, I think, a more even split between the two, because it's the kind of large scale stuff. Then how does MJO help in generating MCSs, particularly during its active phases? Are these usually big connected systems, or do they tend to form as more separated clusters? That's an extremely good question. Do I have a good answer for you on that? Trying to remember whether we actually looked at MCS size. So the paper by Julia Crook on that, I don't think we looked at kind of like MCSs splitting or combining, so how well connected they are. I think we did look at the size, and I'm just now trying to get the paper up on my laptop so I can have a quick look. So do bear with me for one moment. So I'm not going to be able to put this up on the screen, unfortunately, but I could find the link in a moment and put it in the chat. But I think so. Yeah, I mean, in terms of the size of the MCSs does tend to increase in the more active phases of the MJO. So it's not, so in the active MJO, it's not just kind of a little isolated features. So the larger scale, bigger kind of broad scale MCSs are more likely to occur when you're in that active and slightly pre-active MJO phases. So yeah, I think it's these kind of big connected systems that you talk about is what's going on in the active MJO.
All right. So, Sophia, how is it? Is it
Yeah.
okay?
Yeah, it's okay. Thank you, Simon.
You're
Okay.
welcome.
Yeah.
Okay, let's move on to the next one. I think we can go to Pak Edi.
Yeah,
The next one,
from myself.
you don't want to post it yourself, or we
No,
can read it?
I'm chatting on chat.
Okay. Yeah, so we have your question here. Can you explain how does the Vanguard theory reconcile the relative roles of moisture convection feedbacks versus cloud radiative feedbacks in maintaining the MJO envelope? Is one essential, or can the MJO persist without one of them? Okay. Simon, you can see the question, right? The next
Yeah,
one.
I can see the question. Yeah.
Okay.
So
How is it?
the relative roles of moisture. Gosh. I don't know. That's a really good question. Yeah, so I mean, I mentioned kind of near the end, thinking about kind of is our understanding of the MJO propagation kind of sufficient for doing this kind of scalar interaction work, kind of thinking about these physical processes. And I guess I kind of threw that in, but I haven't really thought that much. I haven't kind of actively done any work on that. And so yeah, in terms of how the Vanguard effect actually has an impact on these roles in the MJO propagation, yeah, I don't really know. I think I'm not sure anyone's really looked into that. I think that's yeah, that's something to be looked into, isn't it? But I don't think I really have anything I can say about that other than that's a really good question, and yeah, kind of how these scale interactions kind of whether they actually have a role in the way the MJO propagates in the first place, I don't know. Obviously, for a lot of the MJO's propagation, it's just going over kind of open ocean. It's going over the Indian Ocean and it's going over the Pacific Ocean. And therefore, you don't have any of this vanguard effect kind of involved in the first place. So presumably, the vanguard effect isn't needed in terms of a theory of MJO propagation. It can propagate without it. However, we know that when the MJO is over the maritime continent, it behaves rather differently because you've got the land in the way, because you've got the vanguard effect happening. And people talk about the maritime continent barrier effect, that the MJO is kind of more liable to die out while it's over the maritime continent than while it's elsewhere. And so it seems like the kind of the vanguard effect is probably responsible for that. So I suspect there is probably a role in terms of the specific behavior of the MJO over the maritime continent, but more generally in terms of MJO propagation, it's not needed in order to explain the MJO's propagation. But sorry, that doesn't really answer your question, but I think that's the best response I can give, other than to say that's something interesting to look into.
Okay, Pak Edi, you have respond or
Thank you, Dr.
okay.
Simon, for your explanation. Exactly, I have one more due to the quantitative value. For example, when Bengkulu floods, maybe how much the contribution of MGO, contribution of its equatorial waves, Kelvin, Rossby, or mixed Rossby gravity wave, and also the local effect. Is it possible to make the quantitative value or just description? Or
So,
what do you think, Dr. Simon?
So do you mean
Is it possible to make the quantitative value?
Do you mean
for
quantifying
driver?
So like quantifying the relative effects to see which is the more important, you mean? Or
yeah, I mean, yeah. How much contribution? Yeah. Is it possible? Or
yeah, so if I go back to yeah, I mean if I go back
putus-putus apa itu?
Yeah, so if I go back to here,
Ya
I mean
udah itu aja kalau memang ini.
This was found by sort of quantifying the contributions to the variability of each of the drivers and then picking out any driver whose contribution was above, I can't remember what threshold it was. So in my paper that this came from, I do have a table showing those relative contributions. So I can put the link in the chat. But yeah, so that's again, yeah, I'll type the link into the chat. But yes, so I was able to quantify those and to rank them in order, kind of with the caveat again that I think something wasn't quite right with the Kelvin waves in that paper, that the Kelvin wave variability should have come out as a bit higher. But other than that, yeah, it is possible to quantify these things. And I will put the link in the chat to the right figure for you. yeah, hopefully that answers that.
Okay, so this link is
Okay, Dr.
is
Simon.
your paper, is it?
Yeah.
Okay.
Yeah, I will check on that paper. Thank you very much.
Okay, thank you, Pak Edi. Okay, we have one more. Maybe this could be the last one. Maybe Fadli Naufal. Please go ahead. Fadli.
Thank you, Yuda.
Yes,
Am I audible?
sure.
Yeah, and I appreciate for this amazing talk, and then you did a great presentation. I also have the same question related to the relationship between drivers and the extreme weather, but I'm interested more about the squall lines that you mentioned in this 11th slide, I guess. So my question is, what type of drivers trigger the squall lines the most? And also, in terms of the relationship, how it looks like between the magnitude of the amplitude of the drivers, such as MJO or equatorial lines, and the power or the magnitude of the squall lines. It could be size, it could be the impact of the squall lines. Thank you.
Yeah, thanks. So this is a question which is extremely important to us in Singapore at the moment. So last September, 17th, I think of September it was, there was a particularly intense Sumatra squall. It was an unusual one in that it was in the evening, not in the morning. And it brought particularly strong wind gusts and did some damage in Singapore. And so ever since that case, it's been a major area of interest for MSS as to what actually causes the more intense Sumatra squalls, because we find that we can forecast the squalls, but not necessarily know how intense they're going to be. And particularly, yeah, thinking about the wind gusts, which are the most hazardous thing for us. So I'd say that there's work still going on that at MSS. In terms of the large-scale drivers, I don't think we've managed so far to link the intensity of the squall lines to the drivers. Whether it's true that you'd get, say, let's say for the sake of argument, you're just looking at the amplitude of the MJO, whether that correlates with the amplitude of the Sumatra squalls, I think hasn't been looked at. My guess would be probably not. My guess would be it's more that the MJO or the equatorial waves are kind of a precursor to these things forming. But having seen animations of both individual systems and sort of composites of systems, in the way that they tend to propagate away from the mountains, they reach the Strait of Malacca here, they kind of tend to re-strengthen and reorganize when they get there, and then kind of propagate eastwards and form these kind of nice bow-echo shapes. I suspect the intensity, a lot of it is due to that kind of process of strengthening here, and also just the conditions kind of over and around Singapore, which I guess to an extent could themselves be controlled by the large-scale drivers. But I suspect that the amplitude of, say, the MJO is probably not the more important thing. I think so. I mean, what people have been looking at is, for example, if you look at, because we have Doppler radars in Singapore, so we can look at things like the wind strength around Singapore. Things like, are these kind of things precursors of how intense the hazards associated with these squall lines will be? So I think there's probably a lot more on the local scale. I mean, I'm aware that my whole talk has been saying, well, hang on, the large scale actually determines what's going on the local scale, but I suspect there's a kind of localized things that may be more kind of first order effects. But I think these are questions we're still looking into here at MSS. But yeah, highly relevant questions. But yeah, this study didn't look at amplitudes of these large-scale drivers. Yeah, so we didn't compare sort of weak MJO days and strong MJO days. So we haven't actually done that comparison.
Oh yeah. Can you hold there? Why did you use the 2 hours lag time?
Oh, good question. I can't remember, and don't know. Sorry. I'd have to look that detail up. There may be someone on the call who knows, but yeah, I can't remember. Let's see if I can quickly find. Yeah, I can't remember why we looked at lag 2 hours.
That's totally right. I also have a follow-up question. In terms of the composite over days, did you calculate how many events, or the number of events of the composite from A to D?
So it's the same events that have gone into each composite. There was
okay, yeah, got it. Yeah, okay.
I mean, in terms of the number of events, it was several years of data. So yeah, 33 years of data, and we got, I think there's something like an average of 50 events per year. So there's a few hundred that have gone into the composites, but yeah, it's the same events in each composite there.
Okay, nice info. Thank you so much.
Thank you.
Okay, thank you, Fadli. So we're kind of 3 minutes towards the end of our schedule. There's one question appear in the chat box. Maybe you can have a quick look, and perhaps Simon can just have a quick response, probably.
Vanguard effect. Yeah, so I haven't specifically looked for a Vanguard effect in equatorial waves. I suspect that you would see something. I think you'd only see a fairly small effect if it's there. I mean, if you think of the MJO propagating eastwards, you've got more convergence being formed all the time to its east, and that convergence being shut off to its west, and that's, you know, why the whole thing propagates. That is also going to be true of, say, a Kelvin wave, but obviously the Kelvin wave is much smaller scale and moves through much faster. So although you may well see some effect, I think it's going to be much smaller for these equatorial waves than it would be for the MJO, just on the basis of its scale. Is my answer to that.
Right. Pardi, you have a response, or maybe that's because we're closing to the end of our schedule here. Or maybe Simon, you have more things to share with us, probably.
I don't think I have anything specific other than to say, I mean, some of those things I brought up at the end, these are always things I'm happy to discuss if people want to get in touch. So yeah, it would be interesting to know if, for example, anyone in Indonesia is really thinking about how this sort of information can be made useful for operational forecasters. I think that kind of research to operations is always a really big challenge and something that I'm quite new to. So if anyone has any thoughts on that sort of thing, that would always be really interesting to hear from people and discuss that. Yeah, I think that's the sort of closing thought I'd like to leave people with.
Okay. I think some of the audience could be from the Met Office, and they'll be interested in your idea.
Great.
It's 11 a.m. here and 12 p.m. in Singapore. The end of our schedule. Don't think we should hold Simon's lunchtime. So I think this is a amazing talk by Simon, and it's worth to rewatch again. We have in YouTube, we have that in YouTube Live. We all can rewatch, make notes, and perhaps if there are more questions, I think Simon will be happy to answer probably by emails probably.
Yeah. Yeah.
Okay,
Thank
okay.
you. So, thank you very
Emailnya apa, Pak Yuda?
Yeah, I'll share Simon's email. Or maybe you can
Yeah,
say
please write
yourself.
Simon your
Simon,
email
yeah, put
so
in
we
the
can
chat.
contact you after that.
Yeah.
Mm,
Put it in the chat now. So yeah, thank you very much, Yuda, for the invitation to come and speak. It's been a good opportunity to address you all. And yeah, I've just put my email address in the chat.
It's our pleasure. It's our pleasure here.
Thank you.
Thank you so much. So, okay, there you go. Please take notes, copy it. So here we are in the end of our schedule. Thank you so much, everyone. Thank you, Simon. It's been a great talk, and I think we should follow up with more discussion probably in the future. And that's it. That's end of our forum here. Thank you so much, and have a good day. Goodbye. We meet again in another Colloquium Prima forum. Thank you so much. Thank you so much.
Thanks everyone for coming. Thanks. Bye.
Okay, thank you. Bye.
Thank you,
Thank you,
Simon.
Simon.
Pak Yuda,
Ya, siapa?
saya mencoba share
Hmm.
teman-teman saya yang di luar,
Hmm.
yang di Europe lah.
Hmm.
Kalau diadakan pukul 9 pagi, di sini masih pukul 3, euy.
Gimana Pak? Putus Pak tadi Pak?
Kalau acaranya diadakan pukul 9 pagi,
Ah.
yang di Eropa kan mesti pada pukul 3 pagi ya,
Oh
pada
iya.
tidur nyenyak.
Iya Pak. Lah
Jadi
ini mah buat kita Pak.
disarankan,
Buat kita ini Pak.
enggak maksudnya kan pihak sana juga kan ini diskusi ini sedang hangat ya, membicarakan masalah multi interaksi gitu ya di kalangan Europe, di kalangan Amerika, maksudnya ilmuwan-ilmuwan sana lah ya.
Oh iya.
Pasti banyak teori baru yang masih diperdebatkan ini yang sama
Iya,
Simon.
iya.
Jadi mereka juga pengen tahu sih yang di UK gitu ya. Enggak lah kalau pukul 3, pukul 4 pagi aku masih tidur nyenyak. Nggak mungkin kata dia. Maksud saya jika memungkinkan gitu ya next time itu diadakan pukul 1 atau
Iya,
pukul
iya, Pak.
2 gitu ya. Sehingga
Iya.
yang di sana juga ikut. Saya yakin ini juga mereka pengen tahu kan
Iya, iya.
the recent studies gitu ya terkait dengan MGO dan itu apa ya bela-belanya gitu kan.
Siap, siap. Ya.
Ya, ini
Ya,
saran
next
aja
time
kalau
lah.
memang memungkinkan gitu.
Ya, next time kita undang siapa yang lain, kita pakai shift siang lah.
Ya.
Oke, Pak Eri, makasih banyak Bapak Ibu semua. Sampai
Oke.
jumpa lagi. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Ya. Izin leave.